Yeah.
Yeah, perfect.
Okay.
Great.
So yeah, I won't see anything anymore other than my screen. So please navigate me.
Yes, I will tell you when there is some issue. We have 25 minutes.
Thank you.
Okay, so I am very happy to introduce the next speaker, Maria Kiferova. While the previous speaker was an already shining star of quantum algorithms, Marika is a rising star. Hopefully not a shooting star though. So despite her young age, she's already a permanent research fellow at the University of Technology, Sydney. She's also a part-time member of the Google Quantum AI team. But I think right now you are on a family visit in Slovakia, right?
Yeah, I'm visiting Slovakia after many, many years. So it's
Yes.
really good to be in this part of the world and to also talk to the researchers in Central and Eastern Europe.
Yeah, thanks. So the stage is yours, Marika. Thank you.
Yeah, thank you so much, Zoltan. Yeah, so today I will be talking about some recent work that was done in collaboration with Nathan Wiebe and Carlos Ortiz Morera. And I would just like to highlight that everything that I will be talking about today are my views and research that came from UTS. And this is not a Google talk in any way, shape, or form. So let me start with an overview. There is a very broad audience in terms of interest in quantum computing, so I will try to give as much of a broad introduction as possible. So I will start by introducing generative quantum models and why one might be interested in them. Then I will talk about a massive problem in quantum machine learning known as Barren plateaus. And lastly, I will tell you about our idea about overcoming Barren plateaus that allowed us to learn, sometimes efficiently, thermal states on a quantum computers. So when people try to motivate quantum and machine learning, it usually goes this way. We know that quantum is very powerful. We can factor large numbers efficiently. It's this new, completely groundbreaking technology. And also, machine learning is something that's been very prominent recently. If you use Siri or if you use Google search, you work with machine learning. It's somewhere under the hood. So it's something, even if you don't tend to program neural networks, or even if you don't do anything heads on with artificial intelligence, we all use the products of machine learning. So it seems very natural to take these two very powerful techniques and put them together and hope that the product will be even better than the sum of those two. But it doesn't always go that way. So a big question for quantum machine learning is that whether quantum and machine learning would go together well, such as a pie and an ice cream, or if we end up with some monstrous creation that would be just significantly worse than any other ingredient in it. My personal opinion that it really depends on how one would combine the features of quantum and the features of machine learning. And I hope that I will be able to convince you that at least in some particular ways, quantum and machine learning can really enrich each other. So quantum machine learning has been very popular. I think there are multiple QML talks even at this conference, but there are also significant difficulties at analyzing them using quantum machine learning algorithm. And one of the big problems is that we don't really have a large quantum computer. The machine learning models that people use traditionally usually run on massive clusters, and we have models with millions and billions of units. And this is simply not possible to replicate on quantum computers. We can only play with a handful of qubits, and even then, we will be severely limited by noise. So what we can do instead are two different avenues that can work very nicely in unison. We can do quite a bit of theoretical analysis, which is what Nathan, Carlos, and I did in our paper, and show that certain avenues for quantum machine learning cannot be very fruitful. And we can also show some bounds on what can be done. We can analyze certain parts of quantum machine learning algorithms theoretically in the big O notation. And we can also study some small instance demonstrations. So sometimes even with small instances, we can see that some idea wouldn't work. And we can also use this small numerical simulations to test our intuition. We also won't be able to prove that anything would scale, but it's a nice evidence to complement the theoretical analysis. So the type of quantum machine learning that I am most interested in is when we are learning from, or if we are trying to learn some properties of quantum states. So we are really trying to apply the quantum machine learning techniques and the quantum machine learning algorithms on some quantum states or quantum processes. So one option how we can learn is to learn directly from quantum states. We can have some quantum states coming from some quantum sensors, or let's say they can be an outcome of algorithms for linear systems or differential equations. And then we can use these states as an input to our quantum machine learning algorithm to analyze some of their properties. Alternatively, we can train our quantum computer on some classical data, but in a way that the outcome would be a quantum state. And if we have a quantum algorithm that is able to generate quantum states from some property or from some statistical model, we will call this a quantum generative model. And this is what we're doing in our work. There are different ways how one could build a quantum algorithm, or let's say a quantum machine learning algorithm or a quantum neural network. But one fairly popular idea is to take a classical feed-forward neural network and make some analog of them in the quantum world. So classically, we have some input units that go, the information in the neural network flows to the front, and then we will have some outputs. And the goal of this classical neural network is to learn some weights and biases on these connections between our units. So in the quantum case, instead of the simple weights and biases, our goal will be to learn parameters of quantum gates. We will take a quantum version of a neural network as a simple parametrized quantum circuit. So if we are working with generative model, we can have input of 0, or we can have some input to start with, and then we will have lots of gates with some parameter. And without loss of generality, we will choose our gate to be some rotation around some simple Hamiltonians, h of j, and then our goal will be to learn these angles, theta j's, or you can alternatively think about them as having some Hamiltonians and trying to learn how long do we need to evolve with each individual Hamiltonian. Another key notion in a quantum neural network is an objective function, which we use to measure how good or bad our quantum neural network is. The objective function is just something that we can measure. Eventually, it will be, something that will map the outputs of our circuit to some numbers. And in this case, this mapping would be expectation value of some observable age on the output of our circuit. You can also notice that the objective function can be defined on all the units, or all the qubits, or only some of them. But we are not required to use all of our qubits in the definition of the objective function, or what we will consider as output of our quantum circuit. So we will The notation that I will be using throughout the circuit, throughout this talk, is that I will call visible units the qubits where we will be evaluating the objective function, and any ancillary qubits can be seen as hidden units. So the goal of the training will be to learn some parameterized unitary, so this parameterized circuit, in order to minimize the objective function O. So the big no, so it can be shown that with quantum circuits, we can create distributions that cannot be efficiently reproduced classically, and that's all well and good. But the question is whether we could actually, find these circuits that will lead to very low values of this objective function for the problems we care about. So in other words, could we efficiently train quantum neural networks or models like that? The most common type of training is gradient descent. So let's say that you are in the middle of Australia, and in this beautiful rock called Uluru, and you are trying to get as low as possible. So you are trying to minimize your elevation. And a very easy way to do it is that wherever you are, you measure the gradient in your place, and you will make a step in the steepest possible direction. However, if you find ourselves in an area that is very, very flat, all the gradients will be either zero or negligible, and you won't be really able to get very far. So this type of a gradient descent will get stuck very quickly. And if this happens to a quantum machine learning algorithm, we will say that the algorithm experiences a Barren plateau. So Barren plateaus were first reported by a team from Google quite a few years ago, where Jared McLean and his collaborators show that if you start with quantum circuits that are polynomially deep, the gradients and the variance of the gradient will be decaying exponentially with the number of qubits. So if we, this is really bad, because for many quantum neural networks, we would like circuits that are reasonably deep to model complex phenomena. Even worse, even for some quantum circuits that are very, very shallow, but have a objective function or cost function that is very global, so something like fidelity or some projector on the good state, this will experience a Barren plateau as well. So intuitively, for almost all the states, our objective function will be giving the same value. Almost all states will be equally bad, and then there will be only a very, very narrow region where our objective function would be able to convert well to the minima. And my collaborators, Carlos Ortiz-Marrero and Nathan Wiebe, and I also show that even having a lot of entanglement between our visible and hidden units, so the qubits that we are measuring and the ancillary qubits, can lead to a Barren plateau. So Barren plateaus are very, very common. If you just try to construct a quantum neural network by putting together some gates in a way that it kind of sort of makes sense, I can almost guarantee you that you will run into one of these many types of Barren plateaus. And also, what distinguishes the Barren plateaus for quantum neural networks from vanishing gradients in the classical case is that quantum algorithms typically start at a Barren plateau. So while classical algorithms can have gradients that are getting smaller and smaller, and at some point they cannot be trained very well, in the quantum case, one would initialize the model, and the model will be obviously terrible, and it will be stuck and it won't be able to get any better. So this is a really big problem. It can be seen as a problem of initialization, but it really prevents us to train or learn something from these parameterized circuits. The fact that Barren plateaus are a big problem can be also seen from a beautiful paper by Zoe Holmes and her collaborators. And they show that there is always a trade-off. Under very, very mild conditions, there is always a trade-off in quantum machine learning. So whenever we have a model that is very expressive, it can be, the architecture can be BQP, it can be shown that it explores the entire Hilbert space with a lot of precision, then these types of models also cannot be trained very well. So this is a really cool result. So the question is, can we do anything to either escape a Barren plateau or never experience it at all? And this is the problem that my colleagues and I were trying to tackle. So I already mentioned that we previously worked on a problem where we were looking at the role of entanglement in creating Barren plateaus. And our result had this assumption that the objective function that we are measuring, this Hermitian operator H, is bounded. This is a very understandable assumptions in quantum computing. Pretty much every time we are working with some Hermitian operators with circuits, everything is finite, everything is bounded. And making this assumption that our Hermitian operator is bounded led to showing that the gradient of this objective function, I called it f here, would be decaying polynomial in the dimension of the Hilbert space or exponentially in the number of qubits. But if we now choose an unbounded objective function, so instead of we will give up on this Hermitian operator that we would be measuring completely, we can perhaps circumvent Barren plateaus. Because if we have an objective function that is unbounded, it would violate one of the very few assumptions that exist in all the different Barren plateau results that I talked about. And this is actually a very simple idea, because once you looked at the classical machine learning and just data processing, people there use scale divergence as their objective function. And hopefully we could do something very similar in quantum computing. So let me now reiterate one more time for the people in the back. So the Barren plateau results that we have in quantum machine learning don't immediately apply for unbounded objective function. It doesn't guarantee that anything with an unbounded objective function will work, but we just don't have any no-go results in there. But almost all of quantum machine learning, as we know it now, uses bounded operators. So let's look first to classical machine learning for inspiration. In here, we use a scale divergence as an objective function. And scale divergence very intuitively measures how much information will be lost if we replace our actual data by the model that we are trying to learn. The problem with scale divergence is that it is computationally difficult to compute. So it's NP complete. I think it's at least NP complete, potentially even harder to compute. So people in ML never ever compute the value of the objective function. We will be only computing its gradient through sampling. And the gradient might be, in many cases, much easier to compute through some Monte Carlo techniques. There is an analog of a KL divergence in the quantum world. So if our data is a quantum state and our model is a quantum state, we can use quantum relative entropy to again explain the relationship between the information in the model and in the data. And one can, one can formally sometimes compute the derivatives of quantum relative entropy. However, if we now have some, if we have some hidden units or some, ancilla qubits in our model, this becomes very, very difficult. Very intuitively, it is because of this, we have to do some logarithms of matrices. Everything is not commutative. So if you start taking derivatives of matrices, none of the rules we learn in first year calculus would apply, and one would have to be much smarter. But this is not really practical for numerical methods for machine learning. So we opened some quantum information textbooks and we went out to look for some better objective function, something that can allow us to compute gradients and also that would upper bound the quantum version of the KL divergence. And the objective function that we chose is maximal quantum Rayleigh entropy for alpha equals 2. So this is a pretty obscure information theoretic measure, but it has really nice properties. It gives an upper bound on what we want. It can be in some cases quite tight, but not always. And we can also compute its derivatives easily. They have a closed form. So we can, since this is a divergence, it is not a measure on quantum states because it is not symmetric. However, we are only trying to get to a case where, assuming that both of our data and our model are full rank, they would be equal. The divergence will be 0 if and only if they are equal to each other. So for the purposes of training, we can allow ourselves to swap the order of the data and the model as the argument of the divergence, which will prove to be more practical to work with. And this is the formula for computing the gradients for what it is and inverse Rayleigh divergence. And I will again stress that our algorithm would compute only the gradients and never the objective function. Even this form of the gradients can be computed. However, there are some little bit inconvenience things here, such as inverse of matrices. This can be done through block encoding and quantum singular value transform. However, this will certainly need a large fault-tolerant quantum computer. So I'm running out of time, so let me just share a little bit more insights about training thermal states. So while we can, in principle, use this approach to learn any states, not necessarily efficiently, but we might not experience the Barren plateaus that are common in QML. We were interested in learning thermal states with our approach. And this is because thermal states are very, very common, but it can be computationally very difficult to learn them. So the way how we will be given the thermal state is that we know the Hamiltonian that will define it, and the Hamiltonian would be given to us as a linear combination of unitaries. So we will have access to all of these unitaries as oracles, and we assume that we know all of the coefficients. And the cool thing about our algorithm is that we don't need to compute the partition function. This is because, it's just some nice things cancel out. So we give two algorithms and compute their big O complexities for computing a single gradient. One that uses sampling, and the algorithm is kind of shallow, and one that uses some more advanced techniques such as amplitude estimation and linear combination of unitaries. So I would stress that none of these algorithms can be implemented on the NISC hardware just yet, and this is just a trade-off that we had to do. We had to increase the depth of our circuit in order to compute the gradients directly instead of just estimating some Hermitian operator. So we also we had some rigorous results on the complexity, and we showed what are the necessary conditions for avoiding a Barren plateau in the case of unitary quantum neural network with no ancillas, but we also ran some numerical experiments. And here we show that as we were adding more and more hidden units to our model, we were still able to learn better and better. Our loss function was increasing and our fidelity loss function was decreasing and our fidelity was increasing. This is what you would expect from a machine learning algorithm, but if we didn't employ this Renyi divergence training, we would be running into the entanglement-induced Barren plateaus. So we had some rigorous results, and we also verified them with some small-scale numerical experiments. So to sum up, trainability is a central question in quantum machine learning. If we can't train a model, it doesn't matter how powerful it is, so it's not really useful. But we need to be really careful about constructing them, what would be the architecture and what would be the objective function. Otherwise, we are very likely to run into a Barren plateau. So thank you very much, and I would be happy to answer some questions.
Yes, perfect. Thank you very much. So I'm back. We have this hiding, unhiding method here, which takes some time, fortunately. Thanks a lot, and for this great talk. So there is actually one question from the audience, from Zeki Seskir from Karlsruhe. So in AI and AI ethics, there is the concept of explainability, which in practice is a set of technical constraints on your model. Can we talk about anything similar with quantum neural networks? Is quantum machine learning more or less efficient compared to classical machine learning for constrained models?
Yeah, so there are some numerical studies looking into it, but there is very little we can say theoretically. That's my understanding. So there were many people, with this, trying to take ideas from explainability and different concepts from machine learning, and then they run it on 5 qubits or 10 qubits, and many of them are looking very, very promising. But it's having 10 qubits and having 10,000 qubits is very, very different, and we just don't know how this will scale. So you could compare them, and depending on what exactly you are comparing, they might look very efficient, but again, we can't use this small quantum machine learning model for anything useful. They're just really toy problems.
Thanks a lot. And I also have a question before we wrap up the session. So it's maybe a little bit more broader question. So you had this very nice result about that you cannot say anything about, or you cannot say that strong statements about Barren plateaus when you have these unbounded loss functions. Would you mean that then maybe quantum optics could be a better platform for quantum machine learning, or you had some other things in mind when you are saying that, where you have, for example,
Um,
unbound operators?
Yeah. So, I mean, we were all looking only, at the old school qubits, and you can implement it with whatever you want.
Hmm.
The key here is that we are not trying to evaluate some, unbounded Hermitian operator.
Hmm.
Our objective function is, some type of a divergence, and we are never ever
Sure,
measuring
it's a
directly.
divergence and
Yeah,
it's
maybe
unbounded
if
in that
people
way, but yeah.
yeah, maybe if we start looking at, some tricks from optics and look in analog quantum computation,
Hmm.
maybe that could work. I think it's a really good idea. Again, it's very hard to say how that would be if that would be able to scale up very well, because at some point you will start running into a lot of noise. But it seems like a really cool thing for the experimentalists out there, or the people who work on analog quantum simulators.
Yeah, continuous variable quantum.
Yeah.
Yes, thank you very much, Marika. It was an excellent talk,
Thank you
and
so
we
much.
go.
Thank you for having me.
Yes, so let's go to the next session then. Bye.